Okay, so we'll continue a little bit with the rat race hybrid. I wanted to show you a few more things and also uh, what the response looks like when we put a device. And then after that, we will move on to coupled line based directional couplers. Okay, so need a couple more minutes to draw this out again. I don't know. I thought I saved it, but huh? Is this one? Ring. Oh, excellent. Thanks. Oh, yeah, actually, because you have been using it for that. Okay, so just to remind you again, there is, oh, but this is not the, wait, they're both in the same one, right? Yeah, there you go. Okay, so this is the 180-degree hybrid. It's a circular transmission line with a characteristic impedance of √2 into 50 ohms, so 70.7. We've chosen the design frequency at, again, 6 gigahertz, and it has a total circumference in electrical length of 540 degrees with these distributions here. Port 1 is the sigma port, which gives you in phase and equal power on ports 2 and 3. Port 4 is the delta port. Excuse me. Which gives you equal power, but out of phase outputs on ports 2 and 3. And ports 1 and 4 are ideally isolated. And here is the one set of responses. What is it done? Okay. Yeah, so these are the transmission. So it's 0.7 is the S parameter for S21 and S31, and it's 0 for the reflection on port 1, which is the matching condition, and also the isolation is perfect. You have 0 transmission, and then it gets worse. Okay. So yesterday, towards the end, I showed you this this 3-port version of this device, which I had used in the past. So I want to take a look at that, and also the that extra fat version of the transmission line in between. So let's first look at what happens to the 4-port device if I change that about the circuit. Okay. So that's going to be, so I'm exciting from 4 and going to ports 2 and 3, and I'm not going to use port 1. Right? So I'm just going to disconnect it here. Otherwise, I'll have to renumber all the ports. And if I go, so I think this graph already has the right sets except for the, so I'll disable the S14. So I have S24. So into 2 from 4, into 3 from 4, and of course the reflection on port 4. And at this point, of course, it doesn't look very different. So in fact, I want you to look carefully. I'm going to freeze this. Reconnect that. So you see there is actually a change, but this is happening way far away from the frequency. So at those frequencies is not even a ring, right? It doesn't have any of those conditions, but very close to the center which is the special operating frequency, there is not much of a difference whether I connect the thing or not, because the symmetry is basically maintained most of the time. Okay, so make clear frozen and go back to schematic 2. Disconnect this again. And now let me define I'm just going to change these 2 sections so that I can tune it. We have the phase as well. Phase is right here. We're at 70.7. I'm going to freeze this for the reference. So this is 3-port response, but with the standard parameters. Now I'm going to play around with this. Let's see if something. So I'm reducing the characteristic impedance of that section. And you see that the 2 power distributions actually come a lot closer. So what's happening is the amplitude imbalance is actually reducing. The one I just changed. Okay. It's these 2. So this is the part where I had disconnected port 1. So if you, so this is now port 4 is the input port, and port 2 and 3 are the 2 output ports. So it's the section between the 2 output ports, the smaller section. That's the one I'm changing. Maybe just to remind you. Okay. It's this part. So this is port 4. That's port 2 and 3. Port 1 would have been here, which is removed. So that's the part there. So right now I'm at about 44 ohms, and it looks like it's keeps getting better. Go to, if I remember correctly, it was. It starts to do something strange, but if you focus on the only on the central part, the amplitude imbalance is only getting better. But there's something else happening, which is the isolation. Sorry, not the isolation, the port match on 4, because S44 is, this is S44, right? And it was sort of like this, but it is now getting worse, somewhat worse. But what's the, so let's see, this is voltage, right? So if 0.1 here would mean 0.01 on power. So minus 20 dB is basically 0.1 on this scale. So it's still fairly good in terms of matched if we use the minus 20 dB as our reference point. Stop here at 25. Now, of course, we don't know what has happened to the phase, right? If it's not 180 degrees, then it's not no longer doing what it's supposed to do. So let's check the phase out, which is here. Okay. And that looks like unchanged, right? Nothing happened to this. It's kind of, I was expecting. Why did this not freeze? Maybe because I, right. Sorry, I think there is some unwrapping thing going on here. Right, so this was 70.7, the standard design. Freeze this. Let's go back and check. Okay, I guess I have to be on the graph to freeze it, I guess. No. Okay. So there is a change, but it's not too bad. I guess what we really have to check is what's the difference between these two values, right? Because here visually, it looks like both of them, their slope is changing together, which means the difference should still be 180 degrees. But definitely right in the middle, it's perfectly fine. And out here, it might be worse. So actually, why don't we do that? We can plot this. And I think I've shown you this before, but maybe can remind you how to do manipulations using these measurement equations. So you can now define a variable assigned to a measurement. Right? I think I'd shown you this before. So I go to schematic 2. I define port parameter S24. And I guess the phases were within plus minus 180. So I don't have to do this in complex domains. So I'll just say phase 24 and keep it with the modifier as angle so that I'll just subtract the two angles then. Okay. Do the same thing for 3-4. And then I define an equation. Hopefully this will work. P24 minus P, oh sorry, so P if equal to P24. Now I can go back to this graph and I can add a measurement. Sorry, wrong graph. This one here. And here I have to now choose output equations and then choose the particular output equation window. You can have multiple such windows and then choose the one you want to plot, which is pdiff. Right? And since it's already in angle and subtracted, we don't want to do any complex modification. We just keep it as real part because it's anyway just a real number. Okay, that's important because if you choose angle here, that will try to compute the polar part of a real number, which will be always 0. Right? So let's see if this works. Oh, yeah, nice. Okay. So it's basically 3 degrees phase imbalance. Oh, but wait a second. It should be 180, no? What happened here? 90. So sorry, 90 is the blue, which is the port 2. This is minus 90. But in any direction, it should have either been minus 180 or plus 180. Maybe I have not understood the okay, so there's a better way of doing it. I'll leave it as a complex number. And then I will design this as P2 divided by P4. Okay. So I'll divide these two complex numbers, their phases will get subtracted. But now this is a complex number. So I will have to plot the angular part of that. So now I will choose this. Let's hope this works. Yeah. Okay. So it's like 180 and all the way up till here, it's only about 2 degrees difference. And this is just minus 180, which is the same as 180. Huh? I'm not sure. I think it's something to do with how it manipulates. Even though I have defined it as the angle, it probably did something different. So I just stuck to the complex form and then it was okay. I'm not sure why exactly that didn't work. There must be some rule about how to do these things, and which I've forgotten. Probably better to make this unwrapped, and then you just get a nice 180 especially. Okay, so if we now try to go back to 70.7, let me freeze it again. Then we go back to 60. So even this actually gets better, right? At the edges, it was less than 180 before. If you look at what happens, so this is the normal design, and this is 180 here, but out here it's 176. Out here is 165. But with the 25 ohm, it's slightly higher, right? So this actually makes even this thing better. Now, even though I had done this many years back, we never tried to figure out from some understanding of why this works. Okay, and I still don't know, but maybe we can find out together. So see if you can come up with some explanation for why this actually improves both the amplitude imbalance and the phase imbalance. So you can actually do the same thing here, and we can plot the ratio. This is graph 1:1. So I've not taken the magnitude of the ratio, which should be close to 1. And it's about 3% variation up to 5 gigahertz. So this is already like a fairly large bandwidth, right? So for a device which creates a differential signal over nearly 2 gigahertz was quite good. This is why we were using this, because it was a very simple way And you could make this inside our lab as opposed to purchasing that particular hybrid. So it worked quite nicely, though we never understood why it did so. So that was that. And then I want to now show you that the response of this, when we actually use it for a real purpose, right now we just looked at this in terms of these transmission properties. Oh yeah, there's one other thing, right? So if I now, I had briefly mentioned this yesterday at the end. It's all about the length, right? So I'm going to take port 2 here and introduce a small transmission line. So I'm just adding some length. Even though it doesn't matter, having the reference at the same frequency helps, because we can then compare how does the length is compared to the other sections. Let's start with 0 degrees. Now let's look at the amplitude graph. Let me just clear all the. So this is the modified hybrid with the 25 ohm section. And I'm now going to add a length of let's see what happens here. Did I put it in the wrong place? Oh, actually, yeah, nothing will happen there. Okay. Nothing seems to be happening. Well, will it? It's now lambda by 2 at 6 gigahertz.
This is the idea because the junctions between the different components.
No, that has nothing to do with it.
Last time you said it's because of the taper that we might have to have.
Sorry, you guys are, I don't know of others, but you are remembering the wrong thing. I'm not talking about that. I'm talking about this fact here. I had made a point that these lengths outside, the ones which take me to the actual device. See, right now, if I want to use this to excite some device, these two ports are far away from each other, right? I cannot directly connect this in. So I need to now run a 50 ohm transmission line from there up to the output. In the first simulation, we had put the 50 ohm port right there, right at these points. And then we just check the response. So I have now created an asymmetry where I've connected one port here, but another port after a length of transmission line. And yesterday I said that if these two things go and then they travel different distances, they're going to accumulate phase. Okay. But why is the response here? What I've plotted here is the transmitted power from port 4 to ports 3 and 2. This is not depending on this at all. No, all this, there is no port. There is not, I mean, it's going to port 2 and 3. No? You see, right?
There was port 1 in the picture.
You tell me. Let me give a hint. It's a trick question. Stare at this and tell me what I have done. Will that measurement really depend on what I put here? Sorry? Yeah, but it is adding an electrical length, no? The waves are traveling.
Right now it's 0.
I just put it back to 0. I mean, but nothing is going to happen on this graph anyway. No? I just showed you that nothing was happening. Here. Right. It doesn't seem to have, it's not even like moving a little bit. So there is absolutely no effect of this on this guy. Why is that? Huh? Can you plot 4, 2? I would like you to answer the question, tell me what actually I will see if I plot 4, 2.
Change.
Really? Is it not a linear passive circuit? Remember, so you have to be careful. It's not symmetric S parameters doesn't mean symmetric circuit. Okay, symmetry in a circuit is something completely different. The thing we learned about S parameters is that if you have a linear passive circuit, it has to be symmetric. It cannot be non-reciprocal, right? That's what it means, right? You can't have different propagation in one direction versus the other if you have a linear circuit. So by adding a length of transmission line, I have not changed the linearity of the circuit. So S24 or S42 are going to be exactly the same. Why is this not changing? And clearly it's correct. Will something happen here? Huh? I just changed the plot, no? See, earlier we were looking at magnitude of S parameter. Now I'm looking at phase of S parameter. Again, S24 and S34 and the difference here. If I change this, so I again put it back to 0 here. If I change this, will this change? Given that I just told you this doesn't change, or you just saw that this doesn't change. It should change. Now, can you tell me why that doesn't change? Your answer is sort of in the right direction, but not correct.
So adding link means we are just adding some phase extra. We are not, consuming any power within the transmission line, I think.
Exactly. Nothing is changed from the point of view of those ports, right? The main reason for it is that because it's terminated with a matched load. All the points I was making yesterday had to do with a reflection measurement. We have not set that up yet. It's a matched system. So remember that a 50 ohm with another 50 ohm transmission line connected in front of it just looks like a 50 ohm, right? In the sense that if power leaves there, it doesn't come back. So we are just looking at transmission. So there is absolutely no change here. But you see the effect here, and this is exactly what I was saying yesterday, is that now, and only one of them is changing because that's the one where I have put the extra transmission line, right? As I increase the transmission line, the phase is changing and it's coming closer and closer to the other one. And at 180 degrees, exactly at 180 degree electrical length, the two are identical, right? So this would now look like a power divider with equal phases, okay? But of course, now the phase is not flat. You see this brown curve, which is the difference, was earlier flat, right, across the band. Now it's no longer flat. It's come to 0, but it has this slope because this slope is just the slope of that line, right? The line is not supposed to have a flat phase shift. It gives you incremental phase shift with frequency, okay? So that's just the effect of the line giving you, with some of it being compensated by the rest of the structure. So actually, I don't know, it could be entirely, if I take a 180-degree line, it might just have exactly this phase shift. Okay. So this aspect is what is going to affect if I now look at allow waves to be reflected from the ports, because everything is matched, nothing is crazy is happening. Okay. So to look at that, let me go back to the schematic, reconnect port 1, and let me disconnect. Let me disconnect port 2 and port 3. Okay. So we are back to 0 electrical length here. I have disconnected port 1 and port 3. So whatever appears at port 1 and port 2 is going to be reflected back. And I've reconnected port 1. Okay. Now I will go to the measurement and let me, this is 1 to 1. Let me deactivate this and reactivate the signal going into port 1. Okay. So what has happened? S24, S34, S44. So S24 and S34, which are the transmission, they are now basically 0, right? Because I just disconnected them. It's not even connected. Then I have this one, which is S14, which is still close to 0. It's 0 exactly at the ideal frequency, and it's slightly higher, but not so much. But S44, which was the reflection on port 4, which is basically the matching condition, is now completely become 1, right, at this point. Does that make sense? Let me put this. Does this make sense that S44 is essentially now 1? Right? Because I'm exciting from port 4. It should have appeared at this point and at this point, but now there is nothing there. So it reflects back, but it reflects back with exactly the same phase. So it was initially like this, so it has come back like this. So it reappears on port 4 only, doesn't go to port 1. Right? So now, if I change that cable, that extra length of cable, which is currently set to 0, and you see what starts to happen here. S44 is coming down and S14 is going up. Okay, so this is exactly the situation I was visually telling you yesterday, is that now the system is not matched. The wave which appears here travels a little extra distance. In fact, there's going to be a round trip time now. It's going to be traveling at a distance corresponding to twice the electrical length here. And then it will come back at a different phase. This one reflects with exactly the same phase. So if this changes phase, then it's no longer going to appear only at port 4. The difference between the two will appear at port 4 and the sum will appear at port 1. And if I now set this to exactly 90 degrees, which would mean a round trip of 180 degrees. Is that right? Actually? Mm. Okay, something strange is happening. Think about this. Huh. Okay. This could be the effect of this 25 ohm modification. Let me set this back to, yeah. Yeah, that's the reason. So because I had modified the hybrid, then that simple argument doesn't work anymore. So this is now the standard hybrid, 4 ports. I've introduced an extra length of 90 degrees, and all the power is now going to the isolated port because I've completely flipped the phase. So now the 2 ports have sort of interchanged their roles and nothing comes back on port 4. Okay. So I guess when this thing is 25, then situation becomes sorry, a lot more complicated, because I think the issue is that when the return wave comes back, it sort of sees a very different condition, and maybe that's why this thing doesn't do the. Anyway, this is not supposed to be used with this kind of configuration. But okay, I'm not sure. I don't have a nice explanation, but we clearly saw that that's the reason this is happening. So just to go back to the point I was making is that you cannot have this. So they have to be careful about this mismatches. But otherwise, this is basically good to go. So let me reconnect this. And now, so this is 25. And okay, this is back to, and I will get rid of port 1. Okay. Finally, I'm going to use this to make a reflection measurement. So let me create another schematic. And let me actually give some names here. I'm going to make a simple LC oscillator. Microfarads. So this to be like 4 picofarads. So I'm just connecting a simple LC oscillator directly to a 50 ohm port. This is going to be a reference. New graph. Oh, because that's probably not on the digital nano entry. Why is my mind drawing a blank? So I want 10 picofarads. So that's going to be 0.1 microfarad. No, 101, right? Yeah, but this is 10 picofarads, no? Or no? Oh, there is sorry, there is that many more zeros there. 1, 2, 3, 4, 5, 6. Yeah. Not, yeah. It's around 5 gigahertz resonance frequency. So you remember this curve, right? This goes from plus 180 to minus 180. The point where it crosses 0 is the resonant frequency. We can also look at it in real. In magnitude, there will be no signal because it's a perfect reflector. So everything is same. So maybe let's look at this one. It's easier. Maybe I tune this to make it around 6 gigahertz. Wasn't that? Now I'm going to do the same measurement. So this was a single-ended measurement, right? So port and with respect to ground. I'm now going to use this hybrid which we made, which is again designed to work at 6 gigahertz. So it should be, perfect at this frequency. So we can see how well it works in terms of, how the shape of this resonance looks like. So for that, I'm going to use the sub-circuit thing, which I told you, because I can use one schematic as a sub-circuit in another one. I go here, I take the 180-degree hybrid sub-circuit. And we have to remember the ports. So port 4 is actually the port where we have to do the measurement, right? That's the port we are sending the power. So I'm going to connect port 1 of this schematic to port 4. So that doesn't matter. Port 1 is internally disconnected, so this has no meaning. And then I connect port 2 and port 3 now in a differential fashion. Right? This is exactly what the chip I showed you, the board I showed you yesterday. This one here is doing, except that I have not put these extra arms there right now. Okay. So now let's look at the graph. It should still be an S11 measurement because it's just the reflection from here. It will automatically create the differential signal, excite it, come back. And since this is all the same length, there's no length here. And we are exciting this differentially. Everything should be symmetric. So there should be no intermixing or anything of that sort going on. It should come back here. Let's look at this graph. Whoa. What's this? Huh? Yeah. What do you mean? This is one. I just explained this. It's port 1 in this schematic, right? These numbers have no meaning in this schematic. It only has a meaning in the other schematic corresponding to the hybrid, right? Okay, I know what happened, but
That one should be the
the one is not even connected, right? Here it's not even connected. So if I put a 50 ohm there, it's like putting a 50 ohm to ground on this particular thing. Quiz class. First question is there something wrong? Or can it be wrong? Let's ask it. There is no where's the 180 hybrid? I've removed it, remember? I got rid of it. You can request alternate measurements or views or something to help you diagnose. Absolute of?
S1.
Oh, okay. You want absolute of S1, but let me ask you, what do you expect to see in absolute value of S11? Look at this schematic. This cannot absorb power, right? Now, even this circuit here, the hybrid itself, where did it go? Right? There is no place, the port 1 is not connected. So it couldn't be that the power is being diverted or anything. That cannot happen. So you won't see anything in S11. Yeah. Sorry? Sure. Let me I mean, I just told you that I did a big part of my thesis and postdoc with this circuit. Now, clearly it worked. There's nothing wrong with this. Let me give you some hints. I will go back to the standard setup. And now you really require skills of observation. You have to carefully look at these responses and then compare. Then you might be able to see. And if you still don't do it, then I'll plot them side by side. But hopefully you can plot it, spot it. Yeah. So, okay, this is how phase was. This is how real part was. And this is how the imaginary part was. Okay. Have you guys absorbed it? You can also always sketch it in your notebook as well. Phase. The phase is the one you should really know by now, right? It just looks like this. Okay. I now reconnected it this way. So there's phase for you. The old one is still there. That's the new phase. Let me go to imaginary. Sorry, what was that? It's kind of squashed. That's a good observation. And that's a hint. But squashed is sort of it's just a visual effect here. But
Then it kicks, that's extra information of this.
that's a very good observation. Why is there extra accumulation of phase? And where do you see the extra accumulation of phase from? Like, how are you saying there is extra accumulation of phase?
The variation in the same frequency ranges. Before the phase. I think
Okay.
it's because of the transmission line.
So you see this overall slope here.
Since there is 180 degrees.
Excellent. There is the first main observation is that there is a 180-degree overall phase shift between the whole thing. Why is that? You see that the phase one actually looks the strangest because something else is happening. Let's look at the real part. At resonance, when we looked at the standard one, it went from bottom to top, right? The peak was at 1. Right now, the peak is at -1. So it's almost as if the whole thing is inverted. Otherwise, this part looks fine, right? It looks like what you would expect at a resonance. Then there is some strange stuff going on here, which is why it sort of looks confusing. You can see that in the imaginary part as well, that normally the imaginary part also goes from positive to negative as you cross 0. Right? When we saw the earlier one, this one is going from negative to positive. But most importantly, it goes all the way to ±1, which is what the resonant response is. And then again, it's doing something strange on the extreme side. And Panya correctly pointed out is that what are we measuring? We are measuring the, I should go to this one. I'm measuring the reflection S11 with respect to this point. But the device is here. Earlier, this port was directly connected, so there was no additional length. But there is now a path length from 4 all the way to here through the hybrid. Right? It's not obvious here, but you look at here, there are a bunch of transmission lines. So that means there's going to be a time delay for that signal to go through and come back. And that gives you an additional phase accumulation overall. That's the phase accumulation which is happening as part of the hybrid itself. Okay. That is what is giving rise to this extra variation, which is most obvious in the angle part, because it looks like there's a resonance here, but there is this overall slope. If you remember when we talked about this overall slope in the network analyzer, that you undo this by adding this electrical length, because I said that if you have some sharp feature, you'll completely miss it over this slope. Here, the slope is not very large, so you're seeing some resonance. So in microwave office, there is actually a trick you can do, because you have to cancel the electrical length. You can give a negative transmission line, a transmission line with negative electrical delay, which physically doesn't exist, but mathematically it exists. You can just, if you just write the S matrix with a negative length, the phase will go in the opposite direction. So it compensates for that. So let's see if that allows us to see this somewhat better. Okay, so again, for easy comparison, I will keep this at 6 gigahertz. Start with 0, put a tuner on that. And of course, this has to be 50 ohms because that's just an extension of this 50 ohm transmission line. And let's look at this. Now I want to go to negative directions. So let me set this at 180. Right, okay. Seems like it was not Good enough. It's nice. Looks like you're right. It's about 270. It completely fixes this. Okay. So a large part of this strange frequency variation is just due to an overall delay between the waves going from one to the other. If you remember, when we were looking at the notes in the book for the 90-degree hybrid, the S2 ones and the S3 ones, they were not 0 and 90 degrees, right? They were minus 180 and minus 90. So that's the overall phase accumulation is there. On top of that, there is an additional phase. So similarly, here also we saw it was plus 90 and minus 90. So there was an additional phase accumulation. So that kills it. And then the rest of the variation, which is this little ripple here, this is now you're way outside the band where the hybrid is supposed to work. But right at the middle, it's actually absolutely fine. Right? Looks like a proper. Now let's look at the other things here. Okay. Now looks a lot better. But again, at the end, it starts to do some funny things. And the imaginary part also looks correct. I mean, it has to. Only if the real and imaginary are behaving correctly will your resonance look correct. Okay. So this is the first thing that you will get this electrical delay, but that's just in a real experiment, there's going to be other wires and everything. So this is not really a problem. You just undo that and you get a nice response. Now, let me go back to real part. Yeah, so I'll freeze this. And I'm going to connect. Oh, I see. I put the, okay, I should have put it here, but I actually put it in the hybrid itself, but that doesn't matter. It's effectively the same thing. But I should now set it to, okay, I guess it doesn't matter. I'm going to reconnect in the standard way. And let's now actually compare, since I've frozen it. So that was that other observation which you had, though I don't know whether you meant this or just the fact that everything looked, there were these more variations, so it looks squished. But now I've removed that extra variation, but you see that there is a difference. What does this difference mean? The resonance is falling faster for the hybrid compared to the standard single mode excitation. What does that mean? If it's falling faster, what does it mean for the resonator? Okay, maybe you tell me, why is it falling faster? No, we just, that's an artificial effect, right? It's just an accumulation of, I just removed that and that's how you got the frozen trace. This is real. So this is, what does this represent? This width is the resonance width, right? So it's basically got to do with the sharpness of the resonance, which is related to the dissipation in the resonance. So it's basically looking like with the hybrid, the resonance is sharper than with the 50 ohm port connected. You all already know why this is happening.
In this 50 ohm, there is a resistor.
There's what?
There is a resistor, 50 ohm resistor. That is.
Where is the 50 ohm resistor?
In the port.
Yeah, but even in this case, also this 50 ohm was connected here and then it was going over there. Remember, this circuit inside does not have any resistor. It only has transmission lines. So why is this
RC. So R is C.
so but C is the same, na? C and L are the same. So what does that leave you with?
This hybrid is maybe acting as some this detective even if it's made out of resin case.
Acting like a what?
Like even if it is made out of resin case, it is effectively acting.
This is the circuit we have right now, where this is R equal to 50 ohms. So remember that this is equivalent to, because a voltage source in this model is an ideal voltage source, it has zero impedance. So this is equivalent to having this whole thing like this. So this 50 ohm decides the dissipation. And you remember the, I don't know, I thought didn't we do this, that Q is RC omega 0, quality factor, or omega naught over 1 over RC. So this is basically the resonant frequency, and that's the bandwidth, the full width, half max of this resonance is 1 over RC. So the damping, which is related to this 50 ohm, the fact that it's being driven directly by a 50 ohm source. So I guess we didn't go into this detail, but there is this what appears to be a discrepancy, that when you measure a reflection coefficient from an LC oscillator, it's lossless, right? The LC oscillator is lossless, which is why in steady state all the power comes back. But yet we are talking about a line width.
I think there are two resonances. There are reasons for the circuit itself, and the
You mean for the hybrid?
hybrid, and for the LC, and they are combined to be that hybrid resonance.
No, there is no resonance in the hybrid. Right? We saw its response, right? Remember what the hybrid is supposed
No,
to do.
there are some response there are some peak in the
No, I know what you're trying to say, but there is no peak. We just saw how the response of the S21 and S31 looks like. It just looks flat. And the phase is just going, there is no resonance. You're right that if there were two such resonances, it would give you a much simpler answer. You actually already know this. Somebody said something to this effect in one of the previous lectures as well. Okay. If I want to draw the equivalent circuit for the hybrid case, so sorry, let me finish this. So, right, so this is the fact that it's supposed to be lossless, but yet there's dissipation, because this is basically energy can flow out of this system, right? That is the meaning of dissipation. And the magnitude of the dissipation is basically in this case set by the characteristic impedance of the system, that is a match to 50 ohms. Okay. So the Q factor right now here, the width of that resonance is going to be set by R equals 50 ohms and C equals whatever the C is here. Let me check. It's 7.1 picofarads, right? So if I compute that, so actually probably easier to do it on the calculator because there are 2 pi's involved. So 50 into 7.1 picofarads, so that in 10 minus 12 into 1 e. I can never get this right. Anyway. I guess the thing for making it 0 is not, it's not the 50 into 355. And if I take the inverse of that, where is that? Okay, so this would roughly correspond to I have to divide by 2 pi because this is in there is pi. So this is now in think like megahertz unit. So it should be about 448 megahertz if I remember correctly. Let's look at this approximately if this works. So this is actually the half max point, right? Because it's -1 to 1. So the total height is 2. So half height is 1. So it's basically this point here. So this is 5752. And this is 6203. Okay, so 5752, 750 and 200. So about 450, right? Which is basically what we roughly calculated. Okay, so that's what the width is. What's happening with the height? Start with my 2U. Okay, the sigma code doesn't exist. So I'll just get rid of this. This is 2, this is 3. If I wanted to draw this type of circuit for this one, how will I draw this? Remember, this here, if it's B, then this is plus B over root 2. This is minus B over 2. Right. So if I try to write it something like this, I can do that, right? But what should I put in this box? You know what component goes in the box, right?
It's an output impedance from that port. We have to look from that port.
What is that? Nothing to be calculated. We already know how we designed this. So this hybrid is designed to be 50 ohms on all the ports. This is 50 ohms. This is 50 ohms. So if I now recombine it like this, this is plus V that way, and this is plus V that way. It's minus. So now I get total as some 2V over root 2. But the two resistors are in series. So this is basically equivalent to this circuit, but with a 100 ohm resistor and a different voltage. See, it's actually not the power is conserved, but the voltage need not be, right? Because here the two voltages have to just add because they're equal and opposite. Power adds up to the total power, but voltage doesn't. So this hybrid in this context behaves like an impedance transformed differential circuit. So the dissipation seen by the resonator is when it's connected like this corresponds to a 100 ohm system. So the circuits I showed you yesterday, where I had combined the differential DC and everything, there also it's the same thing. It becomes 100 ohms. And that because it's 100 ohms, and remember the Q factor is sort of 100 ohms is more resistance, but actually it's less dissipation because it's in parallel. The line width becomes smaller and exactly by a factor of 2. So you can see that roughly that. So this was about 450 and this is 5852 and this is 6074. So 150 plus MC 220. So about half of that. Right? So the hybrid does this as well. It gives you this differential excitation, but it now changes the effective characteristic impedance. It doesn't change the characteristic impedance, but the dissipation seen by the resonator is now a factor of 2 smaller because it becomes 100 ohms. And it is entirely because you used, this system was designed to have a 50 ohm output impedance on all of the ports. If you redesign this in some way, where it was the output ports were actually meant to be, say 25 and 25 like that, then this would go back to being standard one. Okay, there is no, nothing is being lost or anything. The power is not because this impedance is different, doesn't matter. It's just how the system feels dissipation across these two ports. Okay, this is not, there's another way of thinking about it is if you think in terms of even odd mode expectations as well. Right? So I could have just this resonator connected with 250 ohm resistance, 250 ohm sources. I can connect something like this. And if I set up the two generators in such a way that they're phase synchronized and produce opposite excitations, then it can excite the resonator. If they do even more excitation, nothing will happen to the resonator because these 2 points will be always at the same potential. In this case, also the dissipation seen by this resonator corresponds to 50 ohm and 50 ohm in series and hence 100 ohms. So when you're using these kind of even odd mode things, you have to be careful about this aspect that you can get a different effective impedance shunting your device in your system. And that's why the resonance is sharper. Okay. How can I, if I really care that my impedance should still be only 50 ohms, one simple way would be to put a lambda by 4 transformer here and transform the 50 to 25. Right. That will of course reduce the bandwidth a little bit, but you can easily do that and get it back. So let's see if we can do that over here. Remember that I cannot do it here because this hybrid is designed for a 50 ohm system. Okay, so if I put something here and I transform 50 to 25, I can do that, but then I'll have to redesign the hybrid for a 25 ohm system. So that is another way you can do the same thing. Now I need 2 impedance transformers. Their frequency will have to be again centered at 6, 90 degrees. Can someone calculate the value for this transformer, please? So I'm trying to transform 50 to 25. Transformer impedance squared is the product of the two, right? So, come on. How much?
35.3.
It did work, but again, there is an additional phase shift, right? Because of the 2 lambda by force, you got additional phase shift. But now you can check, it doesn't matter. I can check this point here. 5762, 6162. So again, about 450 megahertz, which is what we had seen before. Okay. All right. Okay, we can stop here. Any other questions? So next time we will do directional coupler and couple lines. Again, I'm not sure Monday I'll be able to take a class, but I will over the weekend give you the schedule for the rest of the semester. Okay, and I also give you possible dates for the final exam and the assignments as well. Okay, all right, stop here.